Okay, we look at the example 2 for Lambert's cosine law. So now we have two lamps, okay, with 3000 lumens and 5000 lumens are placed at A and B respectively. So we have here A and then we have here B, okay. So these two lamps, this one is the first lamps with the lumens is 3000 lumens, okay. And then the second one, B, is 5000 lumens. Okay, the arrangement is shown in figure below. So C is the midway. Okay, we have the C is the midway between both lamps. So we have to calculate the illumination on the floor at position C. So we have to use this Lambert's cosine law because it has a angle here, okay, between the point source and also the surface here. So the solution of this example 2. So we have to calculate what is the illumination at point C. Okay, first we from here. Okay, this one. The first analysis is we do for the lamps, the first lamp, which is the 3000 lumens. So the triangle here we have like that. Okay, so here is the point A, and then here is the point C, and then we have the degree 1. Okay, so we have to use the equation which is I equivalent to F over D squared. Okay, and then we have to times with the cos theta. So because of we have two lamps, so we has to calculate F1 D1 cos theta 1 plus F2 divided by D2 squared cos theta 2. Okay, so we have the value for the luminance for the first lamps, which is at the point A, which is 3000, but we don't have the value for the distance from A to C, and then also cos theta 1. Okay, so that is because why we have to do the analysis for the triangle at the first lamps. Okay, so this is for the first lamp, which is A, point A to C. So we have the theta 1 here. So from this example, we can see that it given the length here is 10 meters. Okay, so here is 10 meters. Okay, then you can find here, okay, this one is 15 meters. Okay, so 15 you have to divide by 2, so you get 7.5 meters here and 7.5 meters here. Okay, so we know that this one is 7.5 meters. Okay, so you have to find what is A to C, AC. So we have to do like this. Okay, so AC hypotenuse. Okay, AC equivalent to 10 squared plus 7.5 squared. You set 2. Okay, then you can get 12.5 meters. 12.5 meters. Okay. Okay, so we know that from here. one is sorry. Okay, so from the first one, this one is A to C, and then we have the theta 1 here. So we know the length is here is 10, this one is 12.5, and this one is 7.5. Okay, and then you also have to do for the second one here, okay, for BC. So you have here C, you have here B, okay. So this one is theta 2. So from the figure, previous figure, we have 7.5 here, and then we have here we got 7. So how we're to get here? CB is by using this formula. Then you can get BC is 10.26 meters. Okay. And from this triangle also, you can get the cos theta 1. Okay. So cos theta 1, trigonometer. So you just equivalent to 10 over 12.5, and then you will get 0.8. Okay, this one is 0.8. Then the second one is cos theta, equivalent to 7 divided by 10.26. You get 0.6823. Okay, so when you have the value for AC, okay, AC, BC, cos theta 1, cos theta 2, then you can just add all this value in this formula. Okay, so this one is 3000 F1. So this one AC cos theta 1, AC is 12.5 meter squared. Okay, 12.5 meters squared, and then you times with the cos theta 1, which is 0.8, and then the F2 5000 divided by BC squared, which is 10.26 squared, and then times with the cos theta 2, 0.6823. Then you can get you just total up F1, the illumination for AC and also BC. Then you can get the illumination for the total illumination at point C is 47.77 lux. Okay. So there is a lot of types of lamps. For example, in this slide we have 9 types of lamps, which are the incandescent lamps, the tungsten halogen lamps, the fluorescent lamps, and then we have the high intensity discharge lamps, which are the high pressure sodium lamps, the low pressure sodium lamps, the mercury vapor, the metal halide, and then we also have the blended lamps and also the light emitting diode, which is the LED lamps. Okay, we look at one by one for types of lamps. The first one is the incandescent lamps. So this incandescent lamp, okay, this is the figure of the incandescent lamps. It is an electric light with a wire filament heated until it glows. Okay, so the efficiency of this lamp is about 70 to 90% of energy converted into heat, and the bulbs contains vacuum or gas filling. The efficacy is the ability to perform a task to a satisfactory or expected degree. It is similar as efficiency, but it is under ideal and controlled circumstances. So for these incandescent lamps, the efficacy is about 12 lumen per watt. And then the color rendering index is 1A. The color temperature is about 2500 to 2700 Kelvin. And the lamp life is less than 2000 hours. equivalent to approximately about 83 days. Okay. The second one is the tungsten halogen lamps. Okay, so tungsten halogen lamps is an incandescent lamp consisting of a tungsten filament sealed into a compact, transparent envelope that is filled with a mixture of an inert gas and a small amount of a halogen, such as iodine or bromine. Okay, so this tungsten halogen lamps. In these tungsten halogen lamps, the tungsten atoms will evaporate from the hot filament and move to cooler wall of bulb. So the efficacy is about 18 lumens per watt. The color rendering index is 1A. The color temperature is warm and the lamp life is less than 4,000 hours. So the advantages of these tungsten halogen lamps, it is more compact, longer life, more and whiter light. While the disadvantages is it will cost more, increase the infrared light and also the UV light, and also the handling problems. Okay, then is the fluorescent lamps. Okay, so this is how the fluorescent lamps operate. Okay, how the visible light is produced. The first one, this is inside. Okay, this is inside of the fluorescent lamps. So the first one is electron emitted by electron at one end of the fluorescent lamp travels at high speed through the tube until it collides with one of the electrons of the mercury atom here. Mercury atom. Okay, it collides with the electron in the mercury atom. And then step 2, the impact diverts the electron of the mercury atom out of its orbit. When it snaps back into place, ultraviolet radiations are produced. Okay, so this one is the ultraviolet rays are produced. And then step 3, when the ultraviolet radiations reach the phosphor crystal here, okay, the impulse travels to one of the active center in the crystal, and here an action similar to that described in step 2 takes place. So the visible light will be produced. Okay, so the compact fluorescent lamp. There are different types of compact fluorescent lamp, which are the T12, T10, T8, and T5, differing in diameter and efficiency. So most efficient at ambient temperature of 20 to 30 degrees Celsius, and compact fluorescent lamps CFL have much smaller luminaires. Okay, so there are two types of features: the halophosphate and triphosphate. So halophosphate efficacy is around 80 lumens per watt. The high frequency gear increases this by 10%. The CRI is 2 to 3. Color temperatures any. Lamp life is 7 to 15,000 hours. And the triphosphor, the efficacy is around 90 lumens per watt. The CRI 1A to 1B. And the color temperature any. Lamp life is about 7 to 15,000 hours. Okay, then we have the high pressure sodium HPS lamps. This is one of the types of the HID lamps. Okay, so the high intensity discharge lamps. So basically these HPS lamps is used in outdoor and industrial applications. It consists of ballast, high voltage electronic starter, ceramic arc tube, xenon gas filling, sodium and mercury. So these HPS lamps have no static electrodes, and a high efficacy around 60 to 80 lumen per watt. The CRI is 1 to 2, the color temperature is warm, and the lamp life is less than 24,000 hours. Okay. Okay, next HID is the low pressure sodium lamps. Okay, commonly include in the HID family. So you basically this low pressure sodium, you can see at the street light. Okay, street lighting, they use the low pressure sodium LPS lamps. Okay, highest efficacy is around 100 to 200 lumen per watt. Poorest quality light colors appear black, white, or gray shades. Limited to outdoor applications, the CRI is 3, the color temperature is yellow, and the lamp life is less than 16,000 hours. Okay, this is the comparison of the types of lamp. We have the incandescents, the fluorescent lamps, the CFL, the HPMV halogen lamps, high pressure sodium, low pressure sodium. This is the second one is the lumens per watt. Okay, all this is the data. And then we have the color renderings index, CRI, and the typical application of all these types of lamp, and the life of this lamp based on the hours. Next is the mercury vapor lamps, which is the oldest HID lamp. It consists of arc tube with mercury and argon gas and quartz envelope, third electrode, outer phosphor coated bulb, and outer glass envelope. So it has a long life and low initial cost. Very poor efficacy, around 30 to 65 lumens per watt. The CRI is 3, the color temperature is intermediate, and the lamp life is 16,000 to 24,000 hours. Then we have the metal halide lamps. Okay, so it works similar to tungsten halogen lamps. Largest choice of color, size, and rating. The efficacy is much more better than other HID lamps, which is 80 lumen per watt. It requires high voltage ignition pulse, but some have third electrodes for starting. The CRI is 1A to 2, color temperature 3000 to 6000 Kelvin, and the lamp life is about 6000 to 20,000 hours. Then we have the blended lamps. Blended lamps means that there is 2 in 1, 2 light sources in one gas-filled bulb, which contains of the quartz mercury discharge tube and also the tungsten filament. So this type of lamps is suitable for flame-proof areas. It fits into incandescent lamps fixtures. Efficacy around 20 to 30 lumen per watt. The lamp life is less than 80,000 hours. Have high power factor 0.95, and the typical rating is about 160 watt. Okay, and then the newest type of energy efficient lamp, which is very popular nowadays, is the light emitting diode lamps, or the LED lamps. There are 2 types of LED lamps, which are the red, blue, green array, and also the phosphor coated blue lamp. Okay, so this lamp emit visible light in a very narrow spectrum and can produce white light. So normally this lamps also has been popularly used for the street lighting, the highways. So it is basically used in exit signs, traffic signals, and the technology is rapidly progressing. So it also can have a low energy consumption and the significant energy savings around 82 to 93%. And it has the longest lamp life, about 40,000 to 100,000 hours. Okay, next is the reflectors. Okay, so the reflectors is, we want to know the impact, how much light reach on the surface, and is it its distribution pattern. Okay, so there are 2 types, which is the diffuse reflectors and also the specular reflectors. So this one, you can see here the difference of the diffuse reflection and also the specular reflection. So diffuse reflection is the reflection of light from a surface such that a ray incidence on the surface is scattered at many angles. Okay, this one is scattered to many angles rather than at just one angle, as in the case of specular reflection. So the characteristic for the diffuse reflectors, 70% to 80% reflected but declining in time, and that is based on painted or powder coated white finish. While specular reflectors have 85 to 96% reflectance and less decline in time, polish or mirror-like, and is not suitable for industrial open type strip pictures. And then we have a gear. Okay, so gear, the control gear needed for operating lamps performs a number of functions. It ensures that the lamp can be started, and once started, can be operated stably over a longer period of time. The device needed for gas discharge lamps are called ballasts and also the emitters. Okay, so for the ballast, an electrical ballast is a device placed in series with a load to limit the amount of current in electrical circuit, and also it can help voltage build up in fluorescent lights. Okay, and the second one is igniters. Igniters, most of the gas discharge lamps such as metal halide and sodium vapor have such a high internal resistance that they need a voltage peak higher than the normal operating voltage to initiate the discharge. Okay, this one is the recommended light levels. You can see here, for example, general lighting for room areas, for rooms and areas used either infrequently and or casual or simple visual tasks. So this is the lux, okay, the illuminance level that recommended, which is from 20 to 150 lux, and then we can see examples of area of the activity. For this 20 lux, for example, it is suitable for the minimum service illuminance in the exterior circulating areas, outdoor stores and stockyards. And then 50, it is 50 lux, suitable for the exterior walkways and platforms and so on. Okay, this is the recommended light levels by the Malaysia Energy Commission, EC or Suruhanjaya Tenaga ST. So we look on to the example 3. An industrial plant has an incandescent lighting load of comprising 100 numbers. Okay, 100 numbers of 60 watt and also 140 numbers of 100 watts. This one is the incandescent lamps. Calculate the energy savings if each incandescent load is replaced by 1 times 40 watt fluorescent load. Lighting is required for 4,000 hours per year, and the cost of electricity is 22 cents per kilowatt hour. Okay, so we want to replace it with 40 watts of fluorescent light, and then this lighting, this system required 4,000 hours per year, with the electricity cost is 22 cents per kilowatt hour. And then the replacement cost is 13 ringgit point 50 cents per unit. Consider balance consumption as 15 watt. So the given data, 100 watt incandescent lamp is 2200 lumens, and then 60 watt incandescent lamp equivalent to 1320 lumens, while 40 watt fluorescent lamp is equivalent to 2400 lumens. Okay, so the solution is, so this is the solution for example 3. First, we have to find what is the power required by existing incandescent lamps. So equivalent to 100, this one is the quantity, right? 100 quantity times with the watt, 60 watt, okay? And then plus with 140 numbers of lamp times with the 100 watts. So you get 20 kilowatt for the power required by these existing incandescent lamps. Okay, now we want to replace it with the fluorescent lamp. So one 40 watt fluorescent lamp, each will be required to place 100 watt incandescents and 2 of 60 watt lamps as observed from the given data. Okay, it means that if you want to use, okay, first we know that 100 numbers of incandescents is 60 watt, and then we have 140 numbers for 100 watt. This one is the incandescents, okay, the essence lamp. Okay, now if you want to use the fluorescent lamp, okay, if you want to use the fluorescent lamp, from here you can see, okay, so 140 watt fluorescent lamp, the lumens is 2400. So it is equivalent to 100 watt incandescent lamp. Okay, so 2400 is approximately near to 2200 lumens. But for the 60 watt, 140 watt fluorescent lamp is equivalent to 260 watt incandescent lamp. Because of what? The lumens is for 160 watt incandescent lamp is 1320 lumens only. So you have to times with 2. Okay, so this one is 2200 lumens. So this one will be, you have to times with 2, you get 2640 lumens. So it is near to 2400 lumens. So that is why it says here that we required 100, this one, okay, to replace 1 watt incandescent lamp for the only one, and then 2 of 60 watt lamps for the 60 watts incandescent lamp. So we required 140 numbers of 40 watt fluorescent lamps to replace 100 watt incandescent lamps. Okay, so as I mentioned before, so this 100 watt means that we need 100 100 numbers of 60 watt. So sorry, this one, okay, for this one, okay, the second one, for the 100 watts of incandescent lamps, so we also need 140 numbers of 40 watt fluorescent lamps in order to replace the 100 watt incandescent lamps. But for this 60 watt, we need 50 numbers of 40 watt fluorescent lamps to replace 60 watt incandescent lamp. Okay, so here we know that required, required for 100 watt incandescent lamp, we have to replace with 140 numbers of 40 watt fluorescent lamp. Okay, but for 60 watt incandescent lamp, so we need 100 numbers, we divide by 2. Okay, so we just need 50 numbers of 40 watt fluorescent lamp to replace the 60 watt incandescent lamp. So okay, so we have here is 140 plus with 50. So the total number of fluorescent lamps required is 190 numbers. Okay, and then power required for one of fluorescent lamp is 55 watt, including conventional ballast power. So we know that the fluorescent lamp is 40 watt. You have to plus with the conventional ballast, which is 15 watt, then you can get 55 watts for one fluorescent lamp. Okay, so we can calculate the power required for total fluorescent load. This is the numbers 190. Okay, numbers we times with the 55 watts. Okay, because one fluorescent lamp equivalent to 55 watts. So times with the 190, so we get 10.45 kilowatts. So if we compare before this, we use the incandescents, we need 20 kilowatt. But when we use the fluorescent load, we just fluorescent light, we just use 10.45 kilowatt. So we get the annual energy savings there. So how we want to calculate is by using this equation. So 20, the power required for the fluorescent, for the incandescent light, you minus with the power required from the total fluorescent light, and then you times with the 4,000, which is hours per year. Okay, this one is hours per year. Then you will get 38,200 kilowatt hour. This one is the energy saving for a year. Okay, energy saving. So we have to calculate what is the annual cost saving. So annual cost saving, you just calculate the annual energy saving. You times with the electricity cost. Okay, 22 cents. Then you get 8,404. Okay, ringgit Malaysian. And then you have to calculate what is the replacement cost. You have to calculate the replacement cost in order to identify what is the payback period. Okay, so the replacement cost is, we know that the numbers is, the quantity is 190 times with the 30 ringgit and 50 cents for per unit. Then you get 2,565. Then you can calculate the simple payback period. So payback period equivalent to replacement cost. Okay, replacement cost, you divide by annual cost saving. Okay, then you times with 12 months. Okay, so the payback period, you get 4 months. So after 4 months, you can get profit from this system, from this replacement for the fluorescent light after 4 months. Okay, in electrical lighting design, the objective of this electrical lighting design is to get better lighting that can increase the productivity. There are two main questions for the designer. First, choose the correct lighting level, which is the correct lux and also the correct quantity. And then choose the quality of the light, which is the color rendering. Okay, next is the methods of lighting. There are 3 methods of lighting, which are the watts per meter squared, this one method. Second is the lumen or light flux method. And then the third one is the point-to-point method. So we look at the first method, watts per watt square meter method. This is principally a rule of thumb method, very handy for rough calculations and normally for checking use only. So according to the watts per meter squared of area to be illuminated. So that one is the watts per meter squared method. The second method and the most popular method, which is the lumen or light flux method. So this method is a commonly used method in lighting system design. So this method is applicable to those cases where the sources of light are such as to produce an approximate uniform illumination over the working plane, or where an average value is required. So this one is the method that can be used. Okay, and then the third method is point to point method. So this is applicable to illuminate a point due to one or more sources of light is required, normally for high intensity artificial light such as the floodlight calculation. Okay. Okay, for this chapter, we will look onto for the Lumen methods. So Lumen methods, the equation for this Lumen methods is this one. So lumens received on the working plane equivalent to numbers of lamp, this one, n, times the weightage of each lamp, times with the efficacy of each lamp, which is lumen per watt, times with the utilization factor, divide by the depreciation factor. Or you can use because you can use the second equation, which is the number of lamps times with the weightage of each lamps times the efficacy of the lamp times with the utilization factor and times with the maintenance factor. So where maintenance factor is 1 over depreciation factors. Okay. So we look on to first, what is the utilization factor? Utilization factor or coefficient of utilization is defined as the ratio of the total lumens, okay, total lumens received on the working plane to the total lumens emitted by the light source, okay. So we have three types of lighting here. We have the semi-indirect lighting. The first one, semi-indirect lighting. So it is the light comes partly from the ceiling by diffuse reflection and partly direct from the source on the working surface. That we call the semi-indirect lighting. And the utilization factor for this semi-indirect lighting is around 0.25 to 0.35. The second one is indirect lighting. Indirect lighting are fixtures that direct the light upward to bounce off the walls or ceiling to light the room. So this one is the indirect lighting. So the utilization factor is around 0.35 to 0.45. And then the third one is direct lighting. So direct lighting directs the light downward directly onto the surface below. And the utilization factor is 0.5 to 0.55. That is the utilization factor. Next is the depreciation factor. So depreciation factor DF, light emitted by source reduces due to dust or dust decomposition on light. Okay, so dust will absorb some light, and absolute cleanliness is not possible. Hence, we need to consider this depreciation factor. So this is the definition of the depreciation factor. The illumination under ideally clean conditions, okay, to the illumination under normal working conditions. So typical value for this depreciation factor is ranging from 1.2 to 1.4. And then we have the maintenance factor, or we call light loss factor. Okay, this one is MF, okay, maintenance factor, or LLF, light loss factor. Okay, so the ratio of illumination on a given area after a period of time to the initial illumination on the same area. Okay, And then lighting efficiency is seriously impaired by blackened lamps, by lamp light, and by dirt on the lamp reflecting surfaces on the luminaire. The losses are due to the physical changes on lamps, reflecting and transmitting surfaces, ceiling and walls. So maintenance factor is more on the losses. So typical value for this maintenance factor that we can use is 0.8. Okay, we look at the example 4, a lecture hall with dimension of 12 meters long and 12 meters wide. Okay, so we have here, so here is 10 meters and this one is 12 meters long. Okay, so the area will be 12 times 10, so 120 meters square. Okay, so it could be illuminated and the illuminance required, we require 350 lux. So assuming a depreciation factor, so this one 1.2 is the depreciation factor, and then the utilization factors is 0.6. So utilization factor is 0.6 for the lighting scheme design. So if 36 watt fluorescent lamps, we use the fluorescent lamps with 36 watts, which is 75 lumens per watt, were to be used, calculate the number of fluorescent lamps required. So we have to calculate what is the number of fluorescent lamps that required for this case. So this is the solution. First, we have to calculate what is the area of the system of the lecture hall. So as I mentioned before, so the area is 120 meters squared. And then we have the total lumens required. Total lumens required is, we know that this one is the lux unit is lumen per meter squared. Okay, then you can just cancel out, so you got the lumens. Okay, total lumens required is 42,000 lumens. And then as mentioned in the example that we use 36 watt fluorescent lamp with 75 lumens per watt for one lamp. So we times with the 36 watts, then we can get 2,700 lumens per fluorescent lamp. Okay, and then we have to calculate what is the gross lumens output by the lamps. So gross lumen, okay, gross lumen equivalent to total lumens required, total lumens required, and then you divide by the UF, utilization factor, and you times with DF, the depreciation factor. So total lumens required is 42,000, and then you times with the depreciation factor 1.2 and divide by the utilization factor 0.6. Then you can get the total, the gross lumens is 84,000 lumens. So you have to calculate the number of lamps. So you just number of lamps is you calculate 84,000, okay, and then 84,000 is the total lumens, is the gross lumens. You divide by one fluorescent lamps lumens is 2,700 lumens. Then you get equivalent to 32 lamps units for the fluorescent lamp. Okay, that's all for chapter 6. Alhamdulillah, so we have successfully complete our lecture from chapter 1 until 6. I hope that all of you can gain more knowledge on this utilization subject and benefit to all of you. So good luck on your final exam and stay safe Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Thank you.